Greetings, folks. As most of you know, I usually do a preamble at the beginning of these videos. It's good for you to have some clue as to what's about to happen. Turns out, though, that Woody Allen did a movie in 2003 called Anything Else, in which there is a scene that does a really nice job of preambling what we're about to do. Now, Woody and I are like this. Okay, that was supposed to be a joke. Mr. Allen doesn't know me from Adam, but he was kind enough to consent to my using the clip through his manager. And so that's where we're going to begin.
After he'd finish with the school day, we'd meet in Central Park and hang out, and he'd usually expound on something.
You think quantum physics has the answer? I mean, you know, what purpose does it serve for me that time and space are exactly the same thing? I mean, I ask a guy what time it is, he tells me 6 miles? What the hell is that?
This is very clever. He starts off by mentioning quantum mechanics, which lets you know that there's something physicsy about to happen. And then he makes a statement about relativity. Now, quantum mechanics and relativity, they're not compatible theories. But that doesn't matter. The point is, he's letting you know that there are people out there who measure time in terms of distance. He then proceeds to voice the opinion of every intelligent soul on the planet when they first run into this by saying, "What the hell is that about?" By the end of this video, you will understand what it's about. So to get started, I want you to think about a bird's eye view of an ant sitting in a room on the floor, and we're going to watch this ant move across the floor. Once it gets done, you decide you're going to graph his path, and you're going to make the south wall here the x-axis and the west wall here the y-axis, except you're not very bright, and you decide to assign the units for the x-axis to be meters and the units for the y-axis to be inches. And when you get done, this is what your graph looks like. Clearly, this is not very reasonable on a whole lot of levels, but in one way, you just don't mix units this way. So what about a space-time diagram where you have an x-axis and a time axis? And because time is a part of the fabric of space, just as is the spatial x-coordinate, the two ought to have the same units. How can that work? Well, to understand how we might do that, consider a photon moving at 3 times 10 to the 8th meters per second that approaches a 1 meter long track. Let's also assume we have a clock in the mix. Photon passes the origin at t equal to 0 seconds, and as it proceeds, the clock ticks away. After going its 1 meter, the elapsed time is 3.33 times 10 to the minus 9 seconds. To be different, let's now define the amount of time it takes light to travel 1 meter as 1 meter of light time. If we make a run again with the photon passing the origin when the clock starts, except now we have our clock measuring time in meters, with the of light time dropped off for convenience. As the photon passes the origin, the clock starts. And after having traveled 1 meter's worth, the clock reads 1 meter of light time. In other words, by defining the amount of time it takes light to travel 1 meter as 1 meter of light time, we can cleverly define time in terms of meters. Observation number 1. To get the number of seconds in some number of meters of light time, you divide by the speed of light. Don't believe me? Try the math. 1 meter of light time divided by the speed of light gives us 3.33 times 10 to the minus 9 seconds, which is the amount of time it takes light to travel 1 meter. Observation number 2. To get the number of meters of light time in some known number of seconds, you multiply by the speed of light. Once again, looking at the math, speed of light times the amount of time it takes light to go 1 meter, multiply them together, you get 1 meter of light time, just like you'd expect. Significance? Most data is taken in seconds. Space-time diagrams, on the other hand, are drawn with their time axis in meters of light time. That means their time axis is going to be labeled CT, with the T part in seconds, and the CT as a whole in meters, where the of light time is suppressed. So when you see a space-time diagram, which will look like this, its time axis will be characterized by CT in meters. And for those of you who are curious, the why of the diagram's look will be discussed in our next video. Just to be complete, an alternative to writing time in units of meters is to write position units in seconds. A light second is defined as the distance light travels in 1 second. This is a big number. If you take the speed of light, 3 times 10 to the 8th meters per second, multiply by a second, it gives you 3 times 10 to the 8th meters. So an object that travels a distance of 1 light second travels a long, long distance, 3 times 10 to the 8th meters. So if you had a space-time diagram that measured distances in light seconds, it would look like this, with the units of position in seconds. This notation is not often used. A special thank you to Woody Allen for giving permission to use the clip from Anything Else, copyrighted 2002, Woody Allen, all rights reserved. Anyway, folks, that's it.